So we're going to talk about derivative of inverse functions and logarithms. So if f has an interval I as domain and f prime exists and is never zero on that interval, then f inverse is differentiable at every point in its domain, which is the range of f, remember. The value of f inverse prime at a point B in domain f inverse is the reciprocal of the value of f prime at a point A equals f inverse of B. I know that's a lot to kind of take in. So what's looking here is if I have f inverse prime at B, that's going to be equal to 1 over f prime of f inverse of B. Okay? So, which is going to be, so that's really like 1 over f prime of A. So we're looking at kind of using that piece here. So our example is x squared, and then our inverse is the square root of x, right? So if I take the derivative of f prime, that's going to give me 2x. We already know the derivative here, right? So if I take the derivative of this function, I know that it's 1/2 x to the minus 1/2 or 1 over 2 square roots of x, right? We can do that by the power rule. But what this is saying is maybe that inverse is difficult to take the derivative of, okay? Maybe it's really hard to do that. So what I can do is I can find the derivative of the inverse by finding the derivative of my original function. Well, that's 2x, right? And then plugging in my inverse function into it. So this is a composition of functions. So this becomes 1 over f prime of f inverse, so 2 times, because remember my derivative is 2x, so 2 times the square root of x, or 1 over 2 square roots of x. There's my derivative, right? So if I can't take the derivative of my f inverse, I can use this formula here to find it. So what I'm doing is it's a composition of functions. I'm taking the derivative of f, I'm putting 1 over the derivative of f, and I'm plugging in the inverse function. So what does that mean when I have a value? So let's say I'm looking at the value of 2 and 4, right? So I have the point 2, 4, right? So if x was equal to 2, f prime of 2 was equal to 4. That's what I'm really trying to say there, okay? And it actually is the 0.24 also. So when I'm looking at this, if I looked at this prime here, what I could do is I could just find the inverse. So I'm going to go 1 over 2 times the square root of 4, which gives me 1 over 4, which is 1/4, okay? So that's if this inverse is really, really hard to find the derivative of, we can kind of use this formula, okay? Derivatives of natural log. So we did the derivative of e to the x or e to the u. E to the u is e to the u times du dx. So one of the things that I want you guys to understand is that chain rule is really, really important. So here I have the derivative of natural log of u. Well, that equals 1 over u, so whatever's inside the natural log times the derivative of the inside piece, so that u. Okay, notice u will be in terms of x, all right? So here I have the derivative of the natural log of 2x. So my 2x is actually going to be u. So u equals 2x, du equals 2. And so what I have here now is I have 1 over 2x times my derivative here, which is 2. So that leaves me just 1 over x. Okay, so I have the derivative of the natural log. I keep the inside the same, times the derivative of that. Okay, so maybe we should do one more of those. So let's say I have the derivative of the natural log of x squared plus 6. Well, that's going to be 1 over my inside here, my u, x squared plus 6, times my derivative of my inside, which is 2x. Now, a lot of times you'll see this written as du over u. And that's fine. We could put 2x over x squared plus 6. This is probably the way you're going to want to write it anyways. Okay, so du over u makes it a lot simpler. Now, here we have the derivative of a to the u power. So this, remember, this is similar to e dx. So this is where we get that e dx as e to dx. So if I have the derivative of a to the u, I have a to the u times natural log of a du dx. Okay? So when I'm taking the derivative, I'm just going to repeat this. So 3 sine x times the natural log of 3, my base, times the derivative of my exponent. Well, the derivative of sine is cosine x. This is my entire derivative of 3 sine to the x. So I repeat my exponential function here. I take the natural log of my base times the derivative of my exponent. Okay? Now we have the derivative of log, log, instead of natural log. So the derivative of log base a of u equals 1 over u times the natural log of a du dx. Okay? So what I'm going to do is I'm going to have 1 over, I'm going to take this part here. So this becomes 1 over x squared plus 6 times the natural log of my base, which is 2, times my derivative here, which is 2x. Okay? Or 2x over x squared plus 6, natural log of 2. So I could put this as du over u natural log of a. Maybe we should do one more of those just to be on the safe side. So let's say I have log base 3 of x cubed plus 7. So what's going to happen is I'm going to go 1. So that's du over u natural log of a. So on the bottom, I have my u, which is the piece inside, x cubed plus 7. Now I have my natural log of my base, natural log of 3. Now I'm going to take the derivative of my inside piece. So the derivative of x cubed plus 7 is 3x squared. There is my derivative. Okay? Now, I'm going to use an approach of logarithmic differentiation here just to kind of show it to you. Most of you would probably look at that and go, oh, well, I could just use the quotient rule, mix in with the product rule, and absolutely you could, okay? But what we're going to do is we're going to look at using natural logs. So if I actually take the natural log of both sides, what happens is I have the natural log of y equals, and now this all splits up, right? The natural log of x squared plus 1 plus 1/2 natural log of x plus 3 minus the natural log of x plus x minus 1, right? So now, since I have the derivative of natural log, I can actually take the derivative of each of these. So I have the derivative of natural log, which is 1 over y dy dx, right? Implicit differentiation equals, going back here, so I have x squared plus 1, 2x, so 2x goes on top because I'm going to take the inside here, put it on the bottom, take the derivative of the inside, put it on top, plus 2 times x plus 3, and the derivative of x plus 3 is 1, minus x minus 1, 1. Now, I have to solve for dy dx. So I have dy dx equals y, because I'm going to multiply by y to get it out of there. 2x x squared plus 1 over 2 times x plus 3 minus 1 over x minus 1 times y. So I had this y times this whole thing before, right? Now the last thing I'm going to do is just substitute what y is. Well, y was equal to x squared plus 1. So this ends up giving me x squared plus 1 times x plus 3 to the half power over x minus 1 times this whole piece. 2x over x squared plus 1, 2x plus 3, minus 1 over x minus 1. So this whole thing. Now you're probably like, well, that's a lot of work. Well, it's actually not too bad when we're looking at it. Now, is this going to be the same as if I did the quotient rule with the product? Absolutely, it's going to be the same. Okay? So here now I have the derivative. Could I find the derivative at a specific value? Absolutely. I could plug in 0 and find the slope of this at 0. Okay? So we want to make sure that we understand that we can use, that's the nice thing about natural log. We used our implicit differentiation here and found it. Okay, so that's another type of derivative. So we're talking about different types of log functions, natural log, logarithmic functions, a to the u.